So when we start to deal in 3 dimensions, we have an x, a y, and a z, and pretty quickly it becomes difficult to keep everything, these equations get more complicated. When we only have 2 equations and 2 unknowns, an x and a y like this, 3x plus y equals 6 and 2x plus 5y equals 15, it's definitely possible to use algebraic methods to solve this. Things you may have seen in a previous class, things like the substitution method or the elimination method for solving a system of equations. Those work quite well for 2 dimensions, for a system of 2 equations and 2 unknowns. However, when we start dealing with 3 equations and 3 unknowns, or stretching your mind here, thinking about 4 equations with 4 unknowns, or other possible scenarios there. The number of equations and variables and all the coefficients and all that stuff floating around, it becomes difficult to keep track of everything. So this is where we start to introduce matrices. And really, we're not really using matrices the way that they were intended to be used at this point. Matrices, we're just using them to store the coefficients of our equations here. So in any case, let me just go through this the way it's laid out. The dimensions of a matrix are always listed as a number of rows by the number of columns. Alright, so for instance, in a matrix, just to give you an idea of what an example of a matrix, well, this thing down here, this is an example of a matrix. This right here, the number of rows in this matrix, there are 1, 2, 3 rows, and there's 1, 2, 3, 4 columns. So a 3 by 4 matrix, this one is a 3 by 4 matrix. This is one way to specify how big the matrix is, essentially, how many individual numbers it holds. And for now, you'll notice that there are these square brackets on the outside. These numbers that are written in here don't interact with each other in any way. This is just, the matrix is essentially a holding cell for them. It's instead of dealing with 1 number at a time, we're now dealing with, well, I guess 12 numbers at a time for this particular matrix. Alright, so how we're going to be using, how this is going to relate to a system of equations is, what we're going to do is we're going to take and we're going to write the equation in each of the equations in standard form. So the ax plus by equals c form that we saw in chapter 1, and it's helpful if it's helpful if they're all integers. Back in chapter 1 we had the requirement where you had to write it where there was those additional constraints, the all integers with no common factor, and the a had to be bigger than or equal to 0. We don't really care about no common factor or a being bigger than or equal to 0, but it is nice to have everything being integers, because when we're dealing with 12 numbers at a time, it's kind of it's more of a pain in the butt to have, oops, this is not equal to, it's more of a pain in the butt to have fractions floating around also. In any case, what we would do to make an augmented matrix for this system of equations is, first off, put it in standard form, make sure it goes your x coordinates, your something times your x plus something times your y equals something. This, and then we're going to kind of put it over here. So, and the numbers we're going to write in this matrix are just the coefficients. So 3, if there's no coefficient here, that's going to be a 1, and then we're going to do a 6. 3, a 1, and a 6. And you'll notice the 6, it's on the other side of the equal sign. It's this vertical line we tend to put here. That represents our equal signs in these equations. Alright, so 2, 5, 15 looks like this. Alright, that's pretty straightforward. So you can kind of see, if we wanted to give the system of equations associated with this augmented matrix, I guess technically in order for it to be an augmented matrix, it needs to have that line there, but people get lazy. And also I didn't know how to put that in the word processing utility that I was using. In any case, so 3, 7, 4, 10. Well, okay, so you'll notice that there's 3 different numbers on the left-hand side of this equation, because this is where our equal sign is. So I'm going to do 3x plus 7y, and for this third column it's going to be times z, so plus 4z equals 10. That's the first equation. You can see that first row becomes one equation. The second row becomes the second equation. 1x, which I'll just write as x, minus 2y minus 3z equals 6. And then lastly, 0x, which I don't really need to write the 0x. I'll just start off with 4y plus 5z equals 11. So this matrix is just a way for us to store all of that information, again, because there's a bunch of stuff going on here, and it can be difficult to keep track of it all, especially for when we're entering stuff into the calculator. The calculator has a nice utility. If we put it in the augmented matrix in the calculator, it will basically solve it for us, and that's kind of what we're working up towards here. All right, let's give the system of equations associated with this matrix. Let's see. You'll notice there's our vertical line. I am just kind of adding it in here so that there's only one column on the right-hand side of the equal signs. But in any case, we get 1x plus 0y equals 2. And if I rewrite that so I don't have things like multiplying by 1 or adding 0, that line reads x equals 2. The second line, 0x plus 1y equals 3, when I clean that up without multiplying by 0 or adding 1, I get y equals 3. So this system right here, this augmented matrix rather, the system of equations that it represents is actually solved. We know that the x would be 3, the x would be 2, the y would be 3. In other words, I could say the point 2, 3 at this point. So as far as what we're trying to do with a system of equations, we ultimately want it to look like this, where we have kind of a 1 somewhere along here and zeros elsewhere, because we want 1x plus 0y. If there was a z, we'd want plus 0z equals 2. And we'd want it kind of like that. Let's look to see what it looks like when we have 3 variables, though. Well, I guess that's a bad example. That one's not right. Let me make an example here. 0, 1, 0, 0, 0, 1, 0, 0, 1 there. And let's say, I don't know, 5, 0, negative 1. So this augmented matrix here would also represent a solved system of equations. This first equation would be 0x plus 1y plus 1z. I don't know why I said that. 1x plus 0y plus 0z equals 5. In other words, x equals 5. In the second equation, you'll notice the only thing that's non-zero here is the y, and it's 1 times y, so we get y equals 0. And this third line would be z equals negative 1. So, ultimately, when we're trying to solve these equations, we want this sort of pattern to happen. If this was to continue, let's say we had a bigger matrix, I don't know, let's say 10 variables and 10 equations. We're not going to get anywhere near that big in this class, but what you would end up seeing is you would have a 1, 0, 0, a bunch of zeros, and then something non-zero here. Then you'd go 0, 1, 0, 0, 0, 0, 0, 0, 0, and you do something here. This first line would represent x equals, let me give a number in here. Let's say 2, and then 3. So x equals 2. This line would represent y equals 3. 0, 0, 1, 0, 0, 0, 0, 0 with a bunch of other zeros. This one would be maybe a 5. This would be z equals 5. And, well, I kind of ran out of variables here. But you kind of get the idea. Ultimately, what we're after when we're solving these things, we want 1s along the diagonal and zeros everywhere else. That's what we want for the left-hand side of this augmented matrix in order for it to be solved. And in the kind of small cases of a two-dimensional, in this two-dimensional case, you can see it is 1s along this diagonal. When I say the diagonal, I'm talking about the upper left to the lower right, and zeros elsewhere. Here we have 1s along the diagonal and zeros elsewhere. We're not really going to be dealing with bigger matrices, but I just kind of wanted you to see that that is ultimately what we're after in those cases. So let's look to see what happens when we have something that looks like this. We almost have 1s along the diagonals. We have 1, 1, but we have a 0 there. We have zeros everywhere else, though. Let's read off what these equations say. Well, the first equation, this one says 1x plus 0y plus 0z, in other words, just x, equals 4. This one, so 1x plus 0y plus 0z equals 4, which we just clean up to read x equals 4. The second line says 0x plus 1y plus 0z equals negative 5. In other words, y equals negative 5. Let me do it over there. And the last line reads 0x plus 0y plus 0z equals 1. In other words, well, everything over there is 0. 0 equals 1. Well, that's kind of a problem, because 0 is not equal to 1. I don't care what else is going on in this problem. If we end up with something like this is a contradiction. And if you think about where you see contradictions, if you remember solving equations, when you have a contradiction in an equation, it means that there's no solution. This equation right here has no solution to it. Since this equation has no solution to it, you might guess about the entire system of equations. Well, overall, that means there are no solutions to the system. And this is actually one of the ways it might look like when you try to solve a system of equations that has no solutions. It'll look something like this. You'll get ones along the diagonal, except for maybe, I don't know, I guess it could happen on multiple rows. But if you have this sort of contradiction going on here, 0x plus 0y plus 0z equals 1, in other words, 0 equals 1, then that means, well, that's a contradiction, that's never true, which means there's no way to make all of these equations true. Thus, there are no solutions to the system as a whole. Now, the other thing that can happen, I don't know why I don't have an example here, the other thing that can happen is what happens if we go 1, 0, 0, 5, 0, 1, 0, negative 3, 0, 0, 0, 0. Let's think about what this is saying. Well, the first equation says x equals 5. The second equation says y equals negative 3. The third equation says 0 equals 0. Is 0 equals 0 a contradiction? No. No, that's perfectly valid. 0 equals 0 is a perfectly valid statement. But the problem with this is this statement doesn't really add anything. It doesn't add any information. Saying 0 equals 0, you can always do that and nothing else is going to change. So essentially what we can kind of just ignore that equation. Then what you see here is we have two equations. And what we saw, I think it was the last video where I mentioned if we had just two planes in a three-dimensional space, the best we could possibly hope for is having an entire line of solutions. And that's actually what we end up with here. We actually end up with infinitely many solutions. And I'll look at some other cases in other videos, but these are kind of the three different ways you can end up seeing those three scenarios we saw before.